So, we continue then our discussion of the properties of the Laplace and the Z transform, and in particular today we start by looking at the effect of modulations both on the Laplace and the Z transforms. So, for example, let us look at the Laplace transform. Let us assume that the function x t has a Laplace transform given by the expression x s with a region of convergence R. We shall ask what is the Laplace transform of e raised to the power alpha t times x t. Well, let us write down the expression for the Laplace transform of this. Which we might rewrite as now one notices that this is exactly the expression for the Laplace transform of x t with the variable s replaced by s minus alpha. And so, the only change that takes place is that the variable s is replaced by s minus alpha both in the expression as also in the region of convergence. Right. To take an example, e raised to the power 2t, our traditional example u t, has the Laplace transform 1 by s minus 2 in the region of convergence, real part of s greater than 2. And therefore, e raised to the power of alpha t, e raised to the power 2t u t would have the Laplace transform given by 1 by s minus alpha minus 2 with a region of convergence, real part of s minus alpha is greater than 2 or real part of s greater than 2 plus real part of alpha. Needless to say, if alpha is imaginary, for example, if we modulate with e raised to the power j t, there is no change in the region of convergence, although there is a change in the Laplace transform expression. Yes. I must emphasize that it is important to take care of the change both in the expression for the Laplace transform as also in the region of convergence. Both of them are equally important. Right? It is often an error made by the beginner in the use of Laplace transforms that he or she corrects the expression, but neglects to correct the region of convergence, and that can cause serious problems in the subsequent steps. We shall now look at a similar property for the Z transform. For the Z transform, let x n, the sequence x n, have the Z transform capital X of Z with a region of convergence R in Z. In the Z plane. We ask what is the Z transform of alpha raised to the power of n x n. So let us write down the Z transform this expression. Summation on n alpha raised to the power of n x n z raised to the power minus n, which can be rewritten as summation on n x n z alpha inverse raised to the minus n. Yes, z alpha inverse raised to the power minus n. And therefore, the z transform of alpha raised, this can be recognized as the expression, the z transform of x n with the variable z replaced by z alpha inverse. And again one must emphasize that the correction or the change of variable is both in the expression as also in the region of convergence. So, this would be capital X z alpha inverse, with z alpha inverse belonging to R, not z belonging to R. Let us illustrate once again with an example. So, we have 2 raised to the power of n u n with a z transform given by 1 minus 2 z inverse. And a region of convergence mod z greater than 2. We ask what is the z transform of alpha raised to the power of n into 2 raised to the power of n u n. Now, I have intentionally chosen this example because it is also transparent. It can be calculated independently of this property and also verified with this property. So, let us use the property first. The property tells us that the z transform will be 1 by 1 minus 2 z alpha inverse with mod z alpha inverse greater than 2, which can be rewritten as 1 by 1 minus 2 alpha z inverse with a region of convergence mod z greater than 2 mod alpha. Needless to say, in this case we assume alpha is not 0. If alpha is 0, anyway the answer is trivial. If you are multiplying by 0, the z transform is 0. So, there is nothing, in fact that is uniformly convergent all over the z plane, so there is nothing to be calculated. So, alpha is not equal to 0, we assume. As I said, the same expression can be obtained if we combine this into one term 2 alpha the whole raised to the power of n u n. And here it is very clear that the z transform would be 1 by 1 minus 2 alpha z inverse with a region of convergence mod z greater than mod of 2 alpha, which is 2 times mod of alpha. So, this is a transparent example which illustrates that property. It is helpful to look at the properties of the z transform and the Laplace transform together wherever possible. It illustrates certain important similarities and differences. between continuous time and discrete time systems. Now, so far we have been looking at properties where there is almost a parallel behavior between the Laplace transform and the Z transform. We shall now look at an instance where there is a distinct difference, namely the situation where we scale not the dependent variable, but the independent variable of the signal. So, let us look at the Laplace transform first. Let x t have the Laplace transform capital X of S with a region of convergence R. We ask what is the Laplace transform of x of a t, where a is a real variable. It must be a real variable. There is no meaning to its being a complex variable, right? So, a is a real variable. Oh, there is a problem. This region is the region of convergence. So, I will say a is real. Let's not, there is a overload of notation. So, this corresponds to the region of convergence. A is real. Now, let us obtain the Laplace transform of this. Let us write down the expression x of a t e raised to the power minus s t dt. I must emphasize that where unspecified, the limits are on the entire real axis of time. Now, with a change of variable a t equal to lambda. Now, we need to, you see, we can write down. So, therefore, dt becomes 1 by a d lambda. And here we must make the following observation. A can be either positive or negative. If a happens to be positive, then when t runs over the entire real axis, so does lambda in the same order. So, it runs from minus infinity to plus infinity, and therefore, dt and d lambda, d lambda by a coincide, and in fact, we do not need to change the limits, right. If a is negative, then when t runs from minus infinity to plus infinity, lambda runs from plus infinity to minus infinity. But then we also have 1 by a d lambda replacing dt, and a has a negative sign. So, here we might as well write 1 by mod a always and keep the limits of integration the same, right. So, we can rewrite this as integral minus infinity to plus infinity x of lambda e raised to the power. Now, we will rewrite t in terms of lambda. So, that is s by a into lambda d lambda, and by mod a. Again, we assume that a is not equal to 0, which of course it must not be. There is no meaning to making a 0. So, clearly this expression can be identified as the Laplace transform of x evaluated at s by a multiplied by 1 by mod a. Multiplied by 1 by mod a. And the region of convergence is, now we have to be careful, it is s by a belongs to the region of convergence. It is s by a. Of course, we shall see in a minute that here the sign of a does not matter. Well, the sign of a does matter. That is what we shall see in a minute. You see, let us take an example. E raised to the power 2t u t our traditional example, has a Laplace transform 1 by s minus 2 with a region of convergence, real part of s greater than 2. Now, suppose we happen to choose a equal to minus 1, perfectly valid choice. We get e raised to the power minus 2t u minus t. Now, this would have the Laplace transform given by 1 by, see, replace s by a, so minus s. It's minus s minus 2, but it's important, real part of minus s greater than 2. Which implies the real part of s is less than minus 2. That means the real part of s is strictly less than minus 2. Is that right? So, it is very important, the sign is very important in determining the region of convergence. Yes, the region of convergence can change drastically. Of course, one can take simpler examples. For example, one might take a positive here, and you might want to choose, say, 2 times at, where a is positive, and that would be a small change here. It is not a very serious change. But I took an example which illustrates that this can be applied to negative a as well, and when we apply it to negative a, we must be very careful about the region of convergence. As I said, this is one situation where there is a distinct difference between the Laplace transform and the Z transform. And the distinct difference comes not so much from the transforms, it comes from the nature of the signals and sequences themselves. The idea of contracting or expanding or scaling a continuous time signal is well defined and well understood. So, it is meaningful to talk about x of at, where a is real. When we talk about sequences, we have a much more restricted choice of the scaling parameter. So, let xn be a sequence on the index n, which takes integer values. When we scale the independent variable here, it must also be an integer uniformly, and therefore, the only scaling possible is by integers. So, we can scale n So, we can only consider sequences of the form x of capital M n, where m is also in Z, a set of integers. There is no meaning to scale n by a real number. It has no meaning in general. Forget real number, not even a rational number. Yeah, it has no meaning. So, only integers are permitted. The effect on the Z transform is non-trivial.
You miss the values.
Yes. Say that loudly in the mic. Samir has a point. He says there is a very fundamental difference between the discrete time case and the continuous time case.
So we miss some of the values like x of 1, x of 3.
That's right.
If m is 2.
That's right. Consider, you see, what is the fundamental difference between scaling in the continuous time case and scaling in the discrete time case? When we scale a signal in continuous time, we are not losing anything. It's just, you see, the beauty is when we see I mean philosophically, the interval, for example, the interval from 0 to 2 in principle has everything that the interval from 0 to 1 can offer you. That is the basic difference between continuous time and real time. There is a one-to-one mapping. This is a peculiar property of infinite sets. The interval from 0 to 1 can offer you anything that the interval from 0 to 2 can. That is not the case with integers, with discrete sets. When we scale a discrete time sequence, we actually lose points. That is not the case with continuous time. So, scaling is a non-invertible operation in discrete time. In continuous time, if I go from xt to x of 2t, I can come back to xt by operating t replaced by half t. That is a valid operation. In discrete time, that is not true. I cannot scale. For example, suppose I write x of 2n. Suppose I choose n equal to 2. I cannot go back to x of n by writing x of half n. It has no meaning because n cannot be chosen to be anything other than an integer. And therefore, there is a fundamental loss of information or loss of content in the sequence. And that is why I said that the effect on the Z transform is non-trivial. We shall see the effect by looking only at two examples of M. And I put it as a challenging problem to the class to generalize to arbitrary M if you can. So, let us look at just two examples of capital M. We shall look at the example M equal to minus 1 and we shall look at the example M equal to 2. Yes. So, let us consider, let xn have the Z transform x of z with a region of convergence given by R, I am sorry, Z. Maybe for in notation, maybe one can use this for the region of convergence and this for the set of reals. That would avoid confusion. Yeah, this could be used for the set of reals in future. Now, let us investigate the Z transform of x of minus n. Well, x of minus n would have the Z transform given by summation of n x of minus n z raised to the power minus n. But let us put L equal to minus n and note that when n runs over minus infinity to plus infinity, L also runs from minus infinity to plus infinity, right? And we might rewrite this as summation of L over the same range x of L z raised to the power L, which is z inverse raised to the power minus L. This clearly is x of z inverse with z inverse belonging to R. Is that right? With z inverse belonging to R. So, a region of convergence that is to the exterior of a circle now coming to the interior of the circle and vice versa. Yes. So, there is a change both in the expression as also in the region of convergence. Let us take an example. Two raised to the power of n un has the region of has the Z transform 1 by 1 minus 2 Z inverse with a region of convergence mod Z greater than 2. What is x of minus n? In this case, x of minus n would be 2 raised to the power minus n u minus n. And this would be equal to, I mean, the z transform of this would be equal to 1 by 1 minus 2z with a region of convergence mod z inverse greater than 2. Which can be rewritten as, you see, we could multiply the numerator and denominator by half z inverse if we wish to write this in terms of z inverse, right. So, we might rewrite this as minus half z inverse divided by 1 minus half z inverse with a region of convergence. Now, you see, mod z inverse greater than 2 means that mod z is strictly less than half. By rearranging this, mod z is strictly less than half. Now, note what happens to the region of convergence. Two things happen. Yes, the region of convergence was to the interior of the circle, half, not the same circle, right, not the same circle. But now let us take the case of x of 2n. You see, the interesting thing is that this is invertible. This is the situation. This is the one and only one value of m, non-trivial value of m, for which the operation is invertible. So, even if I have the z transform for m equal to minus 1, I can get back the sequence xn from the sequence x minus n, simply by carrying out the same operation again. Now, let us take the case of m equal to 2, where this will not happen, right. In m equal to 2, what will happen? What do you mean? What do you mean by saying yn is equal to x of 2n? What do we mean by saying this? We mean that y of 0 is equal to x of 0, y of 1 is equal to x of 2, y of 2 is x of 4, and so on. So, x of 1 is lost entirely, so is x of 3, x of 5, x of minus 1. Therefore, all the odd points x are lost when you go from xn to x2n. And therefore, we expect that even in the z domain, this non-invertibility will be reflected. Yes. In other words, there is an infinity of sequences xn for which yn is equal to x of 2n. That is what it means when we say it is not invertible. Now, how do we get this sequence? It is interesting. You know, as I said, it is a very non-trivial operation. We will have to go in 2 steps. We will first, let us look at the n axis. Minus 2, minus 1, 0, 1, 2, 3, 4. Yeah? Let us write a little bit on this side. So that now, what are we doing? You see, we have the sequence x. So, let us write x of minus 2. Let me keep them. Now, we will do this operation of, going from xn to x2n in 2 steps. In the first step, we shall keep the even samples and kill the odd samples. By the way, this operation is often called decimation. It's called, for example, here we call it decimation by 2. Decimation is a very cruel word. Decimation means killing. When there used to be wars in the ancient times, in fact, decimate literally means to kill in tens. So there was a practice where the enemy used to kill the opposition in groups of 10 at a time. So, of course, we don't use the term in that sense here. In a sense, we are killing the odd samples here, right? So what do we mean by killing the odd samples? We will replace them by zeros. Now, how can we replace them by zeros? What can we express this operation of replacing the odd samples by zeros in the language of the operations that we are already familiar with? So suppose, what are we doing? You see, one way to think of this is to think of it as adding the negative of this. Definitely we'd like to add, we'd like to add the sample or its negative value. That's right. So suppose we take, can you say that loudly? Can you say it loudly? Yeah. Can you say that loudly? That's a good observation. Yes. So how would we express this operation of killing or decimating the?
Sir, we are multiplying the same sequence by -1 raised to n and then adding them. So
that's
we kill
right. That's perfectly correct. That's perfectly correct. So what we are doing is the following. We are saying take xn 1 plus -1 raised to the power of n. Now, of course, here what will happen is that the odd samples will become 0, even samples will get multiplied by 2. So we can divide by 2 to take care of this problem. So this is what we are doing. Yeah, this is what we are doing. Is that right? This is what we are doing. So let's now, this is something whose Z transform we can easily find based on the operations that we've just developed in the last few minutes. So let the Z transform of xn be x of z with a region of convergence R. The Z transform of this would then be half, tell me, xn of course is xn into -1 raised to the power of n would be x of z minus z, x of minus z by the modulation theorem. So, as I said, the operation on the Z transform is non-trivial. The operation on the Z transform, the effect on the Z transform is non-trivial here. Yes? Yes. Now, what do we do about the ROCs? You see, if you look at it, this of course has the same ROC. As far as this is concerned, minus Z must belong to that region of convergence. Now, what kind of a region of convergence do we typically have? We have a region of convergence between two circles. So, mod of Z is what matters, and mod of minus Z and mod of Z are the same. So, both of these have the same region of convergence, therefore, the region of convergence is the same, right? The same region of convergence. But this is not the end of the story. This is not the end of the story. See, we have not really got to where we want it. What we have done is we have kept the even samples at the even locations. You see, we have kept the even samples at the even locations. What we want to do now is to bring them from the even locations to the even locations divided by 2. So let's understand what we want to do. You see, we want, what we have right now is the following expression: x of minus 2 z raised to the power minus 2 plus x of 0 z raised to the power 0 plus x of 2 z raised to the power 2. I'm sorry, x of minus 2 z raised to the power 2. I'm sorry. X of 2 z raised to the power minus 2 plus x of 4 z raised to the power minus 4, and so on. This is what we have. What we want is x of minus 2. Now you see, the minus 2 point should come to minus 1. So we want it to be x of minus 2 z raised to the power 1 plus x of a 0 point, of course, is at 0, plus x of 2 shall come to the point 1. Yes, plus x of 4 shall come to 2. Is that right? Is that right? So what have we done? You see, you notice that this is actually a function of z squared. This is actually a function of z squared. So we are replacing z squared by z, or in other words, z by square root of z in the expression. Is that right? So what is the z transform that we want? The change that we need to make is that instead of z, we need to write z to the power half here. Not minus z the whole to the power half, but minus z raised to the power half. Yes? So this overall is a z transform, but what about the region of convergence? Z raised to the power of half now belongs to R, whatever it be. Yes, Samir. Yeah, please pass the mic. The question.
So for third order decimation, so can you write xn into 1 plus omega raised to n plus omega raised to 2n?
Very good. So
Proceed.
actually Samir has already answered the challenging problem partly. That's very, very correct. The observation is very, very correct. So here, what is minus? That's very good. That's very correct. So Samir is quite correctly observed. Sorry. That's right. He's very correctly observed that, you see, minus 1 is the second root of unity. And if you take the third root of unity, then you could handle the situation of decimation by 3. In general, if you wish to handle decimation by n, where n is a positive integer, you need to consider the nth root of unity, which is of course the quantity e raised to the power j 2 pi by n. You know, so in fact that's very, very correct. That's very, very correct. So in fact that's an answer. That's an answer to the challenging problem. So in fact what we are doing then, in fact, in general, now he's already given the answer. So you know, when we decimate by n, the first step is to multiply xn by the following sum. Summation k going from 0 to n minus 1 e raised to the power j 2 pi by n k, the whole raised to the n, and divide by n. This is for decimation by n. So in fact, I can straight away, now that he's brought out the point so far, I can straight away write down its Z transform. Now this is often, you see, e raised to the power, I shall use the following notation to denote. I shall call this Wn. I shall call this Wn. Therefore, the Z transform. Now, how will we get the Z transform of a sequence decimated by n? We will write down the Z transform of this, and then we shall replace Z by Z raised to the power 1 by n. By Z raised to the power 1 by n. So, the Z transform shall become summation 1 by n summation k going from 0 to n minus 1 capital X Z omega n raised to the power minus k, with Z replaced by Z to the power 1 by n. So, it is Z raised to the power 1 by n into Wn raised to the power minus k. This is the Z transform of a sequence decimated by a factor of n. Very good indeed. Yes, so we have already answered the question. Very good. Of course, it is a minor change now to get the Z transform when m is an arbitrary integer. We have already taken care of the situation where m is positive, a positive integer. We have also seen what happens when you replace n by minus n. So, it is a to combine these two, and one can get what the effect of any arbitrary integer m. So, we have in fact completed the proof. So much so then for the important properties of the Laplace transform and the Z transform. We have been looking at a special class of Laplace transforms and Z transforms, namely the class of rational Laplace transforms and rational Z transforms. What we mean by rational is that they are a ratio of polynomials. The Laplace transform or the Z transform respectively is of the form ns or nz divided by ds or dz, where ns or nz and ds or dz are polynomials in S and Z inverse respectively. Now, we would like to understand in the next lecture why we give so much of importance to rational Z transforms. Yes, why is it that rational Z transforms or rational Laplace transforms play such an important role in system theory? In fact, as a prelude to that, we shall now record some of the best presentations that were made during the course presentation over the next lecture, that is tomorrow, and perhaps a spillover into the lecture afterwards. I assume that about 20 to 25 minutes followed by 5 minutes of questions should be enough to each group. Is that right? About 20 minutes or 25 minutes followed by a question, about a 5-minute question session could be sufficient for each group. Is that right? Yeah. So then please come prepared tomorrow. The ones who have been identified for making the presentations, are requested to come prepared tomorrow for recording the presentations. All of you must come prepared because it depends on how many are covered in one session. Pay careful heed to the kind of systems discussed there and look at the system relationship, the system description. The key idea is that differential and difference equations are very important in the analysis of systems, and it is from this point that we shall take over in the next lecture to be given by me, whereas we shall have a little prelude before that in terms of presentations made by the students. Thank you. we have been focusing on the rational system to quite an extent, both in the Laplace domain as also in the Z domain. Today we shall look at the rational system itself in a little more depth. In fact, we shall relate the rational Laplace transform and the rational Z transform to the corresponding system description, namely in the context of the Laplace transform it would essentially be akin to a differential equation. In the case of the Z transform it would amount to a difference equation. So, let's come to the system description that underlies the rational system and which explains why the rational system is of such great importance in the whole discussion on Laplace transforms and Z transforms. Now, let us take a simple example. Let us assume we have in continuous time the system given by here we understand y and x both y are both actually xt and yt respectively the input output. Now, if we take the Laplace transform on both sides, we have s plus a into ys is b times xs, assuming that a and b are constants here. So, we have ys by xs, which is the system function, is b divided by s plus a. Now, of course, there is a very close correlation between the numerator and denominator here and the differential equation which one is trying to model, right. It is clear from this example that the numerator of the transfer function, the system function, indicates the derivative operations acting on the input, and the denominator indicates the derivative operations acting on the output. A general differential equation relates a linear combination of derivatives of the output to derivatives to a linear combination of derivatives of the input. And here we are talking about a linear combination with constant coefficients. In that situation, in such a system description where you have constant coefficient linear differential equations, the system function is a ratio of polynomials in S. Yes? In fact, this is a very important class of systems. The class of systems which can be described by, let us give them a formal name, linear constant coefficient differential equations. We shall abbreviate these by LCCDEs. All right. linear constant coefficient differential equations, a very important class of systems. In fact, examples of systems that fall into this class include electrical networks with resistances, inductances, fixed inductances and fixed capacitances, right? They all obey differential equations of this form. A lot of device models also conform to this system description. A lot of electrical devices, in fact, a lot of mechanical devices or a lot of hydraulic devices or thermal devices also have a behavior which is quite closely modeled by equations of this form. So, the class of physical systems that are encompassed by LCCDEs is very wide, and therefore, the rational system plays a very important role in analyzing such systems. In fact, there is another thing that goes in favor of rational systems. If you look at electrical networks, I mean, I am talking about networks comprising of resistances, inductances and capacitances, there is no choice but for the impedance or the admittance, for that matter any transfer function that one has in an RLC network, but to be rational. In fact, you might ask me, what is an irrational transfer function? Can there be an irrational transfer function? We will show that there is a very simple system in the continuous time domain which has an irrational transfer function. Yeah? Let us consider the example of a delay, a simple delay. So, for example, suppose you considered the continuous time system where the output yt is a delayed version of the input, delayed by t0. Transform on both. This is an invariant system, right? It's, and therefore, we can investigate whether we can relate the Laplace transforms of the input and output. Indeed, we can. Ys is e raised to the power minus st0 xs. It is very easy to show that the Laplace transform of x of t minus t0 is e raised to the power minus st0 times the Laplace transform of x. Now, here the system function ys by xs is e raised to the power minus st0, and this is irrational. What do we mean by irrational? We mean it cannot be expressed as a ratio of finite polynomials in S. Of course, it can be expanded in a Taylor series in S, but that amounts to an infinite polynomial expansion, not a finite polynomial expansion. So, irrational systems have a place, but unfortunately, irrational systems also have something esoteric about them in the sense that they are not realizable. You may ask, well, such a system, right, a system that delays the input, a continuous time input by a certain fixed amount, what makes it unrealizable? Well, the problem is, it is possible to approximate the delay within a certain band of frequencies reasonably accurately. So, one can construct continuous time systems whose whose behavior is akin to the delay, but over a certain band on the Fourier axis, on the frequency axis. But to have a delay uniformly at all frequencies is unrealizable. No device can really behave like this in continuous time. Surprising but true. The construction of delays in microwave circuits is a challenging problem. So, to have a uniform delay over a large range of frequencies is often a very important challenge in communications. The challenge is as follows. most realistic systems have a magnitude and a phase response. The phase response is more of a necessary evil, like friction in mechanical systems. Necessary evil in the sense that because we wish the system to be causal, we cannot but have a phase response, though we would have liked the phase response to be 0 if possible. But the ideal phase response is one. What does a phase response do if you think about it? A phase response delays, you see, if you add a phase at a certain frequency, it is equivalent to shifting that sine wave by a certain amount in time. Now, ideally, we would like all sine waves to be shifted by the same amount in time. And that's why earlier on in the course, we had emphasized the importance of linear phase. In fact, if you put S equal to j omega here, you see that if at all it must. Now, for example, if you look at, see, this system, if you substitute S equal to j omega as a phase response given by omega times t naught, which is linear in omega. So, an ideal phase response is a linear phase response, but linear phase is unachievable over the entire frequency axis. So, this is to illustrate that an irrational system is sometimes desired but unattainable, right? Rational systems can approximate irrational systems. For example, one can approximate the ideal delay over a certain range of frequencies with a rational system, right? But that's an approximation. So, here we have, a situation where rational systems are what can be realized. For example, there is a wide class of rational systems which can be realized with RLC networks, right? But the irrational system is sometimes what we strive towards, but we cannot realize ideally. In fact, it turns out that if you look at the ideal filters, the ideal low pass filter, the ideal high pass filter, or for that matter the ideal band pass filters, they really do not correspond to rational systems. I shall try to give you an explanation for it, though not a very rigorous one. Let us look at the ideal low pass filter. The ideal low pass filter in continuous time would pass all frequencies up to a certain omega c and stop frequencies on the angular axis beyond omega c. Now, one thing that makes this response objectionable is the fact that we want 0 as the magnitude response over a whole stretch of the frequency axis. Let me explain why. Suppose, for the sake of argument, we could realize this with a rational system. Now, at what points does the magnitude response of a rational system become 0? At the points where the numerator becomes 0, right, at its zeros. When we have a whole segment of the frequency axis with 0 response, what are we implying? We are implying there is a continuum of zeros. A continuum of zeros is never possible with a rational system, if you think about it. That's, of course, I am not giving a very rigorous explanation, but an explanation that really hints at the reason why this is not realizable with a rational system. In fact, if you go a step further, you can also see that response that is constant over an interval is also not attainable by a rational system, because the argument can be carried by subtracting that constant from the rational system. Suppose you could realize it with a rational system, then that rational system minus that constant would also be rational, but then you are asking it to be 0 over a whole interval, which means it has a continuum of zeros. A continuum of zeros